Ever wondered how a common kitchen refrigerator can maintain sub-zero temperatures using nothing but pressure and physics? Today on Knowledge Hub, we're diving into the hidden refrigeration cycle, quietly running 24/7 in your kitchen, turning a metal box into a precise heat-pumping machine. Refrigerators aren't just cold boxes with a fan, they're carefully engineered systems built around four key stages: compression, condensation, expansion, and evaporation. And it all starts with the compressor. This is a small but powerful electric pump that sucks in low-pressure refrigerant vapor from inside the fridge and squeezes it into a much smaller volume. According to the ideal gas law, when you compress a gas, its pressure and temperature shoot up, so the refrigerant leaving the compressor becomes a superheated, high-pressure gas. This hot gas is then pushed into the condenser coils, the metal grid you can feel warm at the back or underneath the fridge. These coils have lots of surface area, often with thin metal fins and a small fan, so they can dump heat efficiently into the surrounding room. As the refrigerant gives up its heat to the kitchen air, it changes phase from gas to liquid while staying at high pressure. This is condensation, and it effectively stores the heat that was removed from inside the fridge. From here, liquid refrigerant reaches the expansion device. This can be a capillary tube or a thermostatic expansion valve, and this is where the real temperature drop happens. The expansion device is basically a tiny restriction. When the high-pressure liquid is forced through it, the pressure suddenly drops. When pressure falls, the boiling point of the refrigerant plunges, so part of the liquid instantly flashes into a very cold mixture of liquid and vapor. This ultra-cold refrigerant then flows into the evaporator coils inside the freezer and fridge compartments. Here, the physics of latent heat takes over. As the refrigerant evaporates back into a gas, it needs energy to break the bonds holding it in liquid form, and it absorbs that energy as heat from the air around the coils. That heat is coming directly from your food, your drinks, and the air inside the fridge, so their temperature drops. Small fans blow air over the evaporator, distributing cold air through channels between the freezer and the fresh food section, while carefully designed ducting and vents ensure your ice cream doesn't melt and your vegetables don't freeze. Meanwhile, temperature sensors called thermistors are constantly feeding data to an electronic control board. When the internal temperature rises above the set point, the controller starts the compressor. When it gets low enough, it shuts it off, creating an efficient on-off duty cycle. Many modern fridges use inverter compressors that can vary their speed instead of just switching on and off, which reduces energy spikes, improves temperature stability, and cuts noise. Around all of this, thick polyurethane foam and tight rubber door gaskets act as thermal armor, slowing down heat leaks from the room into the cold interior. Some fridges add automatic defrost heaters that periodically melt ice off the evaporator, so it doesn't get clogged with frost and lose efficiency. Even the choice of refrigerant is carefully engineered. Older systems use gases like R134A, while newer domestic fridges often use isobutane, R608, which works efficiently, household pressures, and has a lower environmental impact when handled correctly. Combine all of these elements: the compressor boosting pressure and temperature, the condenser dumping heat to your kitchen, the expansion valve dropping pressure to create extreme cold, the evaporator absorbing latent heat from your food, plus fans, sensors, insulation, and smart electronic control, and you get a refrigerator that constantly moves heat from the inside to the outside, creating the feeling of cold without ever making cold in the first place. So, if you enjoy learning the engineering behind everyday machines, don't forget to subscribe to Knowledge Hub for more deep dives. And as always, stay curious.